the second, 3 at the third, and 2 at the fourth. So from the statistical mechanic or statistical thermodynamics, okay, this is how we express or the equation for entropy, which is equal to K ln W, where K is the Boltzmann constant with this value, and ln W is the number of ways. So to calculate the number of ways W, okay, it is given by n factorial. So capital N represent the total number of particles. So in this case it would be 12. Divide with the number of particles occupying the 0, first, second, and third energy level. Okay, but some books would call this 0 as 1, 2, 3, and 4. But it is carrying the same meaning. Okay, it's a matter of labeling. But take note the most left-hand side would be representing the lowest energy level, followed by the higher energy levels. So in this case, it would be N0 would be equal to 5 factorial, multiply with 2 factorial, multiply with 3 factorial, multiply with 2 factorial. Just follow the question. And the answer would be 166320 for the W. So you can go back to the main equation, okay? Entropy will be equal to K ln W.
Hello, Doktor.
Yes.
Doktor lupa nak record.
Oh, saya memang tak record.
Oh, tak record
tak record. Okay.
Tak, sebab ada kawan saya, dia tak masuk.
Tak cakap apa-apa pula, tak datang. Saya memang tak record, tapi saya memang akan bagi jawapan akhir dekat spektrum. Okay.
Okay.
Okay. So siapa yang dah datang ni, tolong ajarlah kawan yang tak datang tu. Okay.
Okay, Doktor.
So the unit should be joule per Kelvin for Boltzmann constant, okay, with this value, multiply with the ln W, and the final answer would be 1.66 times 10 to the power of negative 22 joule per Kelvin. So this is the common unit for an entropy. So a straightforward question. Okay, question number 2. A population of 1 million particles, so this tells you that this is total number of particles, the capital N, has 2 energy states available to it with the change between energy state has the value 5 times 10 to the power of negative 21 joule. So whenever you see statement 2 energy state, this is the energy difference. Straightforward, you should be able to imagine something like this, and this is the splitting between the 2 energy state, which is 5 times 10 to the power of negative 21 per joule. So what are the values for each energy states? So simple assumption, you can always assume the lowest energy state or the ground state equal to 0 joule, and the higher one would be 5 times 10 to the power of negative 1 joule. Because we know that the difference between energy state 1 and energy state 0 would be equal to value given in the question. Okay, and the 1 million particles, okay, should occupy only these 2 energy state available given on the question. So 2A, calculate the population of the levels for temperature 300 Kelvin and 3000 Kelvin. So population means that number of particles for each particular energy state. So okay, so it can be represented by N. N is actually representing the number of population or the number of particles in each energy state. So Ni, okay, the subscript I just to indicate which energy level. which energy state or energy level can be N0, N1. Okay, so in this case just N0 and N1. So this is actually from the lecture note. If you add asterisk, it also can represent the Boltzmann distribution. So from this general equation, okay, capital N, which is the total number of particles, okay, multiply with exponential negative epsilon I over kT. So epsilon is energy state value, right? I represent which energy state? Is it the zero energy level or the one or energy state level 1, okay, over kT. Divide with summation of all exponential negative epsilon 1 over kT. So by definition, this is what we call as Q, molecular partition function. Molecular partition function is a summation of exponential of negative epsilon I over kT. So calculate the population means that you are going to first calculate the population for the lower energy level and the higher energy level. So this is one way. I'm sure some of you found alternative way to solve it. As long as you obtain similar answer, it should be fine. Okay, but I prefer to use the one that I introduced in the lecture notes. So calculate population for lower energy state. This equation, see, for the I represent it with 0, okay, and the denominator, it's a total, right, between the two energy state. So it should be expressed exponential negative epsilon 0 over kT plus exponential negative epsilon 1 over kT, because we are going to total out contribution from both energy level. So carefully insert the value. This is the total number of particles, 1 million, multiply with exponential 0. Why 0? Because I assume that the lower energy level has 0 joule. So 0, exponential 0 will be equal to 1. Okay? 1 multiply with 1 million, you obtain 1 million for the numerator. How about your denominators? Okay, exponential 0 due to the 0 joule from the lower energy, plus exponential negative 5 times 10 to the power of negative 1 joule. This is from your energy state level 1. Okay, divide with K, the Boltzmann constant, multiply with T, the temperature, 300 Kelvin. So I'm solving for the 300 Kelvin system first. So the population at the lower energy level would be 769, 742 number of particles. How about the higher energy state? You can do as simple as 1 million, deduct with the value. Okay, you should be obtained 230258. Or you can do step by step as well. Okay, you use the main equation and insert carefully. See, now the numerator is for epsilon 1 system. Divide with the total contribution from both energy state. The value should be the same, 230258. So you can see here, naturally, okay, we should expect that the lower energy level would have more number of particles compared to the higher energy state. So here the value makes sense. How about the population at much higher temperature, which is 3000 Kelvin? So you are going, I'm using the same step, but instead of 300 Kelvin, I'm replacing with 3000 Kelvin. So the value, okay, you can do this on your own. The value for lower energy state would be 530,134. Okay, and then the 1 million minus this value, you should be able to obtain this value for the higher energy state population. Or you can do step by step like this. So if you compare your answer for 300 Kelvin system and 3000 Kelvin system, you can see that at this higher temperature, both energy states are almost equally populated. It's almost right. Less number of particles at lower energy level because most of them have enough energy due to the higher temperature to go to the higher energy levels. So more molecules can reside in the higher energy level. So it makes sense. You should expect as the temperature is getting higher, the population of energy state would be equal if it's two energy state level. Okay. 2b, what will be the population as the temperature approaching infinity? So approaching infinity means that it's getting towards the higher value of temperature. So again, based on this equation, okay, you can replace it, temperature with infinity. Mathematically also you can prove it. You note that beta is equal to 1 over kT. Okay, that's why we have this equation. So temperature infinity, something divide with very big number, you will obtain 0, right? Something divide with very large number, yeah, approaching 0. That's why you get exponential 0, which is equal to 1. 1 multiplied with n, okay, divide with exponential 0 plus exponential 0. So n divide with 1 plus 1, 2, n over 2. Same goes for the higher energy population, also n over 2. So that's why both energy level almost equally populated as the temperature approaching infinity. You can see this effect in the first question. Okay. Question number 3. Define the most probable distribution n with asterisk. Okay, this is a summary of from the lecture note. Okay, if all distribution of a given thermodynamic state are equally probable, then the most probable distribution for the state is the one with largest value of W. This can be represented by the following equation. Okay, so this is what we have used for question 2. So you may define, this is the original equation, but don't forget beta is equal 1 over kT, so you can replace it into here as well. Okay, and you can make some note that this denominator is actually your molecular partition function, which is represented by summation of exponential negative beta epsilon I. Question number 4. Okay. An isolated system contains only 4 particles. So it already implies that the total number of particles, capital N, is 4. And the total energy, represented by capital E, is 4 epsilon. So I don't give value this time, I just represented the total energy as 4 epsilon. Okay, if the only possible energy levels are 0, 2 epsilon and 4 epsilon. So this is a 3 energy level system. So question 2 is the 2 energy, but in this case it's 3, 1, 2, 3. Give all the possible energy configuration that can satisfy this condition. Okay, you have to satisfy based on the question. The energy configuration must made up from 4 particles, and the total energy should be equal to 4 epsilon. And this is each energy level being represented by this value of energy. Okay, lowest one 0 epsilon, the first one 2 epsilon, the second one 4 epsilon. So note that this is what the actual definition, right? Total number of particles means that you sum up Ni from each energy level. For the total energy, it means that the summation of Ni for each energy level. So it will be Ni epsilon I. And in this case, it should be equal to 4 epsilon. And in this case, it should be equal to 4. So based on this condition or set, okay, let's say you put 3 particles at 0 epsilon, the lower energy level. 3 minus 0 epsilon will be equal to 0, plus, remember it's a summation. There's no particle in the first energy level, so 0 multiplied with 2 epsilon also equal to 0, right? And the second energy level, okay, 1, you have 1 particle, multiply to satisfy this equation, multiply with 4 epsilon, it will be equal to 4 epsilon. That's why you obtain the total 4 epsilon. So this energy conversion can be written as 3, 0, 1. So this is the one of the possible energy configuration. And here next, try to put two molecules at lower energy level. 2 multiplied with 0, 0, and then put another 2. At the same time, put another 2 at 2 epsilon energy level. This will be 4 epsilon, and 0 particle at 4 epsilon energy level. Again, you obtain 4 epsilon. So this is, you write this arrangement or configuration 2 to 0. Some students write the other way around, which is wrong. Okay, we always write the lower energy level at the bottom, and you should write in terms of energy configuration format, you should write the leftmost. Okay, so this is wrong, this is wrong, this is correct, this is correct. Okay, so if you try to put other energy configuration, for example 1, 1, 2, it will not satisfy. It will satisfy the total number of particles, but it will not satisfy the total energy. So it's a wrong energy configuration. Only these two energy configuration can meet the requirement for this question. So 4B, okay, based on the energy configuration, identify the most probable configuration. For 301, remember, this is how you determine whether it's most probable configuration or not. You can recall back the Boltzmann distribution definition. It is the most number of ways, right? This is how you calculate numbers of ways, and factorial divide with NO factorial multiplied with N1 factorial multiplied with N2. It will be equal to 4. For 220 energy configuration, it will be equal to 6. So this is the highest value for W for this system. So it's the most probable energy configuration. 220 is the most probable energy configuration. Then calculate the entropy of this configuration for the system. Usually it will refer to the most probable energy configuration. So use this equation S equal to K ln W. The final answer would be 247 times 10 to the power of negative 23 joule per Kelvin. So question number 5. If the molecular partition function Q is given as Q equal to Q trans multiply with Q vibrational multiply with Q rotational multiply with Q electronic, explain or prove how the above equation is obtained. So actually the molecular partition function that we're talking about is due to contribution from various mode of motion. Okay, depending on temperature. If the system is at room temperature, mostly it will only have translational motion. Okay, and again depends on the molecules itself. Okay, as the temperature increases, it will start to have vibrational. Okay, and then depends on the molecule, it will have rotational and electronic. So most of the time, it will be just have translational mode of motion. So, but to go back to this question, how to prove this relationship? Okay, we know that the energy level for each level, okay, also equal to the contribution for each modes of motion. Okay, translational, vibrational, rotational, electronic. Where EI is total various mode of motion. So we go back to the equation for molecular partition function. Right, this is the general expression for molecular partition function. So I just replace epsilon I with this one, so it appears like this. Okay, and here negative in bracket. Okay, I just remove the bracket, so it become negative minus 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 over KT, mathematical rearrangement. So this also actually can be written as follow: summation of exponential negative epsilon I trans over KT dot, okay, summation of exponential negative epsilon I over vibrational, rotational and electronic. So it's a dot product. It's a dot. Okay. So since Q is equal to this, we also can say that Q will be equal to Q trans multiply with Q vibrational, multiply with Q rotational and Q electronic. Question number 6. So similar as question number 4, I add some another problems there. So an isolated system has only 3 particles. So total number of particles is 3. Okay, and the total energy is 4 epsilon. Okay, find the most probable distribution if the only available energy levels are 0, epsilon, 2 epsilon, 3 epsilon, 4 epsilon. So this is 5 energy level system. So you have to find out what is the most probable distribution. Okay. And then second question, state how do you modify this problem if each level is doubly degenerate. So if we have to consider the degeneracy, how the value would be. Okay, but we solve for the first part first. So this is how you can represent the whole question, the whole for this system. Okay, 0 epsilon, epsilon, this is 1 lah kan, 2 epsilon, 3 epsilon, 4 epsilon. Okay, the 3 particles need to be arranged in these 5 energy levels, and it should meet the total energy criteria and also the total number of particle criteria. So if you have 2 particles in 0 epsilon energy level and the third particles in 4 energy level, you will obtain 4 epsilon, the total energy. And this arrangement is be written as 2, 0, 0, 0, 1. Okay. Similarly, next energy configuration that can meet the total energy and total number of particle criteria is when you have 1 particle at 0 epsilon and 2 particle at 2 epsilon. Okay, you can try, okay, to calculate it, and this is how you write 1, 0, 2, 0, 0. Next, okay, put 2 particles in epsilon energy level and 1 particle at 2 epsilon energy level, you will obtain 4 epsilon. So this is how you write it, 0, 2, 1, 0, 0. And next, if you put 1 at 0 and epsilon energy level, 1 at epsilon energy level, and 1 at 3 epsilon energy level, also you obtain total energy for epsilon. So this is 1, 1, 0, 1, 0. Okay, but the question asks you to find the most probable distribution, or synonymous as most probable configuration. Therefore, okay, don't forget you have to calculate the numbers of ways. Okay, for the 4 energy configuration, this gives the highest value of W. So therefore, we can say that 1, 1, 0, 1, 0 has the most probable configuration or distribution. State how do you modify this problem if each level is doubly degenerate. So I don't cover degeneracy concept, but I just want to tell you that it can happen that way. Okay, if each level is doubly degenerate means that you will have each of these energy level is doubly degenerate. Okay, there are more energy levels. Okay, yes, you can see it that way. This is the equation of calculating W, the number of ways, would be like this. The n factorial multiply with the product of gi to the power of ni divided with ni factorial. Gi is degeneracy, so in this case gi will have the value 2. Okay. For 20001 energy configuration, this is how you calculate the W for doubly degenerate. N factorial, the total number of particles, 3. Okay, this is product, that's why it means that you are going to multiply for each of these. This is not summation. Summation means that you add up, right? A product, K means that you multiply. So this is mathematical symbol, okay? So 2 to the power of 2, because you have 2 here, right? Okay, divide with 2 factorial, multiply with 2, now you have 0, divide with 0 factorial, 2 to the power of 0, divide with 0 factorial, times 2 to the power of 0, divide with 0 factorial, multiply with 2 to the power of 1 divided with 1 factorial. It will be 24. So do the same, use the same equation for the other energy configuration. You can see that the number of W, okay, the 11010 will remain as the most probable energy configuration. It's just that the value is different when if it has degeneracy. Okay. Question number 7. Define the partition function Q, molecular partition function. Okay, give the information which may be obtained from it by examining its limiting behavior. So this is actually available from your lecture note. So the definition of molecular partition function, okay, you can give this equation for it, okay, summation of exponential negative beta epsilon I. In other words, molecular partition function tells you how many energy levels is being occupied by particles. That's not simplified definition of molecular partition function. I think I put that in the lecture note. Okay. And what are the limiting behavior of Q? Okay. Limitation property of molecular partition function. You have two conditions. First, when temperature approaching 0 Kelvin. Okay. And second, what happened to Q when temperature is approaching infinity? Okay, we look at first condition first. When temperature approaching 0 Kelvin, it's a very low temperature value. So remember that beta is equal to 1 over kT, right? So that's why you can make use of it makes sense to relate or to have these two conditions relating to temperature. So when temperature is approaching 0, if you go back to your 1 over kT term, kT is 0, 1 divided with very small number or approaching 0, it means that you obtain large number, right? Infinity. Beta will be infinity. This is simple mathematical logic. Okay. Something divided with approach 0, you obtain large number. So when you have beta is very large number, exponential of it, you will obtain Q equal to 1. So T approaching 0, Q will approach to 1. What does it tell you? It means that at lower temperature, only the lowest energy level will be occupied because the molecule don't have enough energy to excite to the higher energy one. So it makes sense that as T approach 0 Kelvin, Q approach 1. Only the lowest energy level is being occupied. So this is the justification. Every term in sum is 0 except the lowest energy level. So here, the lowest energy level, of course, this is where initially all the particles reside. But here, the exponential negative infinity is actually equal to 0. So 1 plus 0 plus 0 plus 0 plus 0, because it's summation, right? It will just give you equal to 1. Okay. When temperature approaching infinity, okay, we go back to your beta, 1 over kT. Okay, 1 divide with large number, infinity, right? Something divided with large number, the final product with the final answer would be very, very small. That's why beta will approach 0. Okay, so if you go back to your molecular partition function, the summation, okay, remember the lower energy level always have the value 1, okay, plus exponential 0, which is equal to 1, okay, 1 plus 1 plus 1 plus 1 plus 1, keep add up due to the different energy level. You will see that Q will approach infinity, a larger number as temperature approach infinity, which makes sense. Okay, the higher the temperature, the particles have enough energy to go to the to occupy or to reside in the high energy level. So these are the limiting behavior of Q. Write a short note on the following: canonical partition function, and how is this related to the molecular partition function. Again, this is a summary from your lecture note. Okay, so canonical partition function is for non-interactive particles such as ideal gas system, which has internal structure where the total energy comes from a contribution from the various mode of motion these particles are usually assumed as indistinguishable. So for canonical partition function, it is being denoted by capital Q. Okay, for the small molecular partition function is for the NBE system, and canonical partition function is for NBT system. Okay, and for indistinguishable systems such as gas, okay, indistinguishable means that you can no longer identify the identity for each particle. For example, in gas, it moves randomly, right? You can no longer trace the identity for each individual gas, so it considered as indistinguishable system. So this is how you relate the canonical partition function with the molecular partition function. Capital Q equal to small q to the power of n, and again is the total number of particles divided with n factorial. So n capital also referring to the total number of particles. So Q is the molecular partition function. Okay. For distinguishable system or localized particle where you still can identify the identity of each particles, just like in the case of solid. A solid don't move randomly, right? It's in ordered position. This is how you relate the canonical partition function with molecular partition function. So you can write that about canonical partition function. So for B, the total number criteria and total energy criteria. So we have covered this in question number 4 and 6. Total number criteria is fixed due to isolated system. It is equal to summation of Ni. The total energy criteria is also fixed, and it can be calculated by summation of Ni multiplied with epsilon I. Question number 9. So we are now still on partition function, but now we have we'll see what's the difference of molecular partition function in translational mode, vibrational, and rotational. Okay, so calculate the partition function of hydrogen atom gas within a container whose volume is 1 meter cubed at 300 Kelvin. So if you look at the question, it already tells you a hint that you should solve for Q for translational, because you are given the information on volume and temperature. This is how molecular partition function for translational mode of motion looks like, right? Q trans equal to V divided with lambda cube. So lambda is actually representing H over 2 pi mkt to the power of half. H is the Planck constant. 2 pi mm is the mass. Okay, it should be in SI unit, kg. K is the Boltzmann constant. T is the temperature. So my tips for you to solve this calculation for Q trans is make sure everything in SI unit so that you can easily cancel off. Okay, because molecular partition function should be unitless. Okay, it shouldn't have any unit. So here we solve for, this is the equation, let's solve for lambda first. Okay, lambda would be, so I convert joule into SI unit, it would be kg m square s negative 2. Okay, and the s here, 2 pi m, so m, mass, so molar mass of hydrogen atom gas. So I give hint here, hydrogen atom means that it's one single molecule, it's not hydrogen gas H2. So molar mass of hydrogen atom, you can use 1 gram per mole or 1.08 gram per mole. I accept both. Okay. Convert it to SI unit, it would be 1 times 10 to the power of negative 3 kilogram per mole. So what is the mass? So to determine the mass of hydrogen atom, as simple as dividing it with Avogadro number, right? Avogadro number is 6.022 times 10 to the power of 23 per mole, and this should be the value, 1.66 times 10 to the power of negative 27 kg. K is the Boltzmann constant, is the value, and I convert joule into kg m square s negative 2 SI unit per Kelvin. and multiply with temperature. Temperature should be in Kelvin, so 300 Kelvin. So if you are given in degrees Celsius, don't forget to convert it into Kelvin. So you can solve all these questions. Can see here, kg multiply with kg to the power of 2, multiply with half, you obtain kg. So kg can be cancelled off, right? I'm cancel off the unit first. M square divide with m square m square multiply with, not multiply to the power of half, you obtain m square divide with m, that's why you have the unit m, okay? And then Kelvin, per Kelvin, multiply with Kelvin, you obtain 1. S negative 2 multiply with S, so and S negative 2 to the power of half, you obtain S negative 1. So you can cancel off with these two. Okay, so you should be able to obtain lambda in the unit of meter here, and the magnitude. So you have to solve by using calculator. This one divide with this magnitude value. The value will be 1.01 times 10 to the power of negative 10 meter. Don't forget to solve for Q. You have to the power of 3. You have to cube it. Okay. Volume has is given in the question 1 meter per cube. So you can easily cancel off the unit. The value would be 9.76 times 10 to the power of 29. For translational mode of motion molecular partition function, you should expect that the value is very large number, because for translational mode, most of system molecules will have translational mode of motion, okay, and at ambient temperature it can occupy most of the energy levels. Okay, so many energy levels available to be occupied by molecules having translational mode of motion. So question number 10 also, translational partition function for a D2 molecule. So D2, see this is molar mass, don't forget it has 2, and this is the molar mass of a deuterium molecule. So the molar mass in SI would be 4.032 times 10 to the power of negative 3 kilogram per mole. Convert to mass with similar step. Okay, as question number 9, the answer would be 7.835 times 10 to the power of 26. You can see it's still a very large number. So we look at question number 11 on rotational partition function. Calculate the rotational partition function for a non-linear molecule whose sigma is equal to 5 at 25 degrees Celsius, given the rotational constant as follow. Okay. For rotational mode of motion and rotational partition function, note that it has different equation for linear and non-linear molecule. Okay, so for this question, we are solving for non-linear molecule. This is how the equation looks like for rotational partition function of a non-linear molecule. So you need info on sigma, K, T, H, C, and the rotational constant. Okay. Again, tips, convert everything into SI unit so that you can cancel off all the unit. And in this case, rotational constant, rotational partition function would be have the value 525 or 5.25 times 10 to the power of 2. Okay, so it's 100. Okay, compared to the traditional, it's much smaller value. Okay, here note that most students will make mistake here. This is per centimeter. So please, your homework is to convert per centimeter to per meter. It should be the opposite as conversion of centimeter to meter. Question number 12. If the partition function for rotation and vibration are given by this equation, okay, what are the assumptions to arrive at this equation? So this equation only valid if you have exceed the characteristic temperature. Okay, it has to exceed the characteristic temperature of rotational and vibrational mode. So in other words, it means that at certain, for each system, nitrogen gas, hydrogen gas, carbon dioxide, it will only have rotational and vibrational mode of motion at certain, if it has exceed certain temperature value. Okay, or else it will just have translational mode of motion. Give the characteristic temperature for rotation and vibration. So it should be equal to this. Okay, this is given in the lecture note. What information will you get from the characteristic temperature, the number of field, rotational and vibrational energy levels? Once it exceeds this characteristic temperature, you can know the number of field, rotational and vibrational energy levels respectively. So I think that's all for tutorial 1. Okay, don't forget to record today's attendance. And next week would be the test. Okay, so the test will cover from lecture 2 until lecture 5. It will take maximum 40 minutes. Okay, kalau dapat submit awal lagi bagus. And note that it will be under e-invigilation, means that you have to be online through Google Meet and turn on your computer. Okay, so I will give detailed instruction about the test via WhatsApp group. Any other question? Kalau tak ada soalan, we can dismiss the class and see you again next week for the test. Okay, so get ready how to turn on your camera, okay, while answering your test for next week. Thank you all.
Thank you.